Right. All right. So this morning, well, good morning again and welcome everyone. So this morning's class, we're going to look a little bit at something called a transfer function realization, which is really how you would tend to implement a particular discrete type transfer function if you have to put it on a computer or embedded system or something of this sort. What we're doing, of course, is a general simple structure, but if you have a processing algorithm, even on your phone, for argument's sake, where you want to take audio in and do some sort of manipulation with it, how you would approach it is basically how what we'll be talking about this morning. All right, the broad sort of approach to taking to implementing a transfer function of some sort. All right, so systems can be described in a number of ways. And of course, we've already looked at the Fourier transform way and recently just refreshed our mind about the Z transform way. And basically, you could describe the same system in terms of its transfer function. And of course, if it's a discrete time transfer function, it's in terms of Z, the variable Z. Its frequency response, which is a function of capital omega because it's a discrete time. So this is really the DFT of it, right? The pole zero arrangement, which is something that you all would have known from your controls and way back when. But in our particular case, in the discrete time case, remember the poles and zeros, the relationship of the poles and zeros, especially the poles, the stability, is that for something to be stable, the poles have to be inside a unit circle. All right. So you could describe a system in terms of that. You could describe it in terms of its impulse response in time. Remember the transfer function. If you remember from signals and so on, this is the sequence. If I put an impulse, I have a system and I put an impulse, a unit sample in, right? Then what I get out are a series of values, right? This is the this is the HN here, the impulse response. If I take the Z transform of the impulse response, then I get the transfer function, right? You remember we did that in signals and systems as well. So that's another way. All of them describe the system in the same exact way. So the transfer function and the impulse response, one is the Z transform of the other, or Hn is the inverse Z transform of Hz. All right. The frequency response, remember we saw it yesterday, so I'll put it here again, right? To go from Hz to H omega, you make the substitution Z equal E to the J omega. So it's the same information. The pole zero arrangement, you remember, if you take the transfer function, the same Hz here, and you take the transfer function, you could get something in terms of Z, you could factorize it in terms of a whole series of poles and zeros, and that is, and then you could plot that and see where the poles especially lie. And then, of course, you have the input-output difference equation. Remember that Hz is really, or let me put it back where, is really Yz is equal to Hz multiplied by Xz. So Hz is Yz divided by Xz. And if I take the inverse transform of that, I get the input-output difference equation, right? Or block diagram, which is what we're going to talk about in this lecture as well, right? All of them describe the same systems. Yeah? Let me know if you didn't recall something or something doesn't make any sense. You have to talk to me because I'm not seeing our chat right now, okay? Usually now, because, well, for this part of the course now, we're dealing with essentially filter design, discrete filter design. So usually your design for a filter begins with some frequency response requirement. You want it to pass some frequencies, stop some frequencies, and so on. How we do that, we'll see in subsequent lectures and so on. But usually, what you're starting with is a frequency response requirement. If it was a controls course, then you would be starting with things like a response time, um, a stability issue, or something of the nature. All right. So you start with a frequency, some requirement, and then from that, remember that gives you H omega, right? So if I give you the frequency response requirement, you have H omega here. From H omega now, we look and see, well, what is the best approach to design a filter to give me that H omega? And we're going to talk about that in subsequent lectures. And then from that now, I get the transfer function of the filter. And then from the transfer function of the filter, I could look at it in all these different ways to see if it does what I want, the HN, if the impulse response is what I want, or if the poles lie within the unit circle, or the input-output difference equation. We'll see where that comes in a while. And the block diagram representation, which shows us something about how the processing will take place. Right? So the next few lectures, we're looking at specifically the ones in the topics in the dotted box there. All right. So let's see how this is going to work. So assume that somehow we came up with our transfer function. Don't ask me how. We started with some description, and we landed up with this thing that you're seeing on the screen here. What I want to find out now, so that's HZ. So I want to find out the impulse response, and I'm assuming that the system is causal. So Hn, the inverse Z transform of that, remember now that the getting an inverse Z transform means looking at the transfer function. Of course, it has to be a proper transfer function. In other words, the order of the denominator has to be less than the numerator. Sorry, the other way around. The order of the numerator has to be less than the denominator. All right, so in a case like this where they're equal, we're going to have to divide it at least once. So the first step, and this was things that we did before, you express it in partial fractions. You have to divide at least once. So you're going to get this off in, this is some a plus b over 1 minus 0.8z minus 1. And then you solve for a and b, the usual approaches that we have sorted out already. And as I told you, if for some reason you're uncomfortable using z minus 1, you could let something like m be equal to z minus 1 and then work it out. But then remember to substitute back at the end. All right. Z minus 1, as you will see in a couple of slides, means something very specific to us as usual. So we prefer to retain that. If you solve it, you should get that A is minus 2.5 and B is 7.5. And then you could read off the Z transform of that, or you can go to the tables, right? And if you do that, the inverse transform of that, Hn, is minus 2.5 delta n. So this is a plain number, gives you an impulse. And then this now is 7.5 by 0.8 to the power n. And because it is, they said that Hz is, what do you call it? Causal, we have to put the unit, the proper way is to multiply that by un. Okay, this ensures that Hn will be, in fact, a causal response. Everybody following so far? At least the technique, if you forgot, right? If you have forgotten at least how to do the mechanics of it, right? So from this, before I go ahead, from this I could find out any value. For instance, H10 will be, well, delta n only exists at n equal to 0. So H10, for instance, will be 0 plus 7.5 into 0.8 to the power 10, whatever that happens to be. And you could work out that. H15, H2, so you can get all of the values of the impulse response. This is the transfer function itself, but the actual values of the impulse response, we can substitute values of n into that and see what happens. As you can tell, this is a decaying exponent. So when n, it's only when n gets very, very large that this now starts to get negligible. So a response like this technically is what we call an infinite impulse response, because it will go on. This technically never becomes zero. It becomes very, very small as n gets huge, but how small it gets and how much information you can store really depends on what you're using it for. So for all intents and purposes, this will go on forever, generate large numbers of values. So this type of transfer function is called an infinite impulse response type. Yeah. Okay, so if I have that now, what is a difference equation that satisfies n? In other words, this is the general form.
So
Uh-huh.
So for the part of minus 2.5 with the impulse, it won't be minus 2.5?
No, remember this is the impulse is 1.
Yeah.
This value only has a value of 1 at n equal to 0.
Oh,
and then it's
okay.
0 everywhere else. So
Right,
at n equal to 10 is 0. Yeah?
Yeah.
Right. Good. So let's see. Okay, so this now is giving me all the values, but let's see what is a difference equation. You remember the Z transform is a way of solving a difference equation for us. In other words, like how you would have, if I were to give you a HS equal to something, then you could find HT, which would be a differential equation that in time behaves the same way as HS behaves in the S domain. So let's see if we could find the equivalent difference equation here. So to do that, we start with HZ again. We can rewrite it just by cross multiplying. HZ is equal to, well, HZ into 1 plus 1 minus 0.8Z minus 1 is equal to 5 plus 2Z minus 1. So put HZ on one side and everybody else on the other. And then you read off the transfer function, the inverse transfer function directly. Remember, from every time you get a Z minus 1, it is something delayed by 1. So in other words, the inverse Z transform of this expression here, HZ, of course, the inverse transform of that is HN, 0.8 Z minus 1 HZ is the Z minus 1 HZ means that HN has been delayed by 1. That's where the Z minus 1 came in, and of course it's scaled by 0.8. 5, a constant, so that's the inverse transform of a constant is an impulse. And then 2Z minus 1, again, this is a constant with a delay of 1 on it. So that the impulse here, the response here is 2 delta n minus 1. All right? You can read it straight off. And that is why, just go back, that is why we prefer to keep this nomenclature, the negative indices, because every time you see a Z minus 1, whatever was before the Z minus 1 is, or whatever, sorry, is not before, whatever is related to the Z minus 1, like in this case, this or a number, is delayed by 1. If it was Z minus 2, it would have been HN minus 2. Yeah? Make sense? We're beginning to ring a bell now?
Yes, sir.
So the input output, okay, so the difference equation, HN, that describes this transfer function is 0.8 HN minus 1 plus 5, an impulse at time equal to 0, plus another impulse at 2 equal to 0. at n equal to 1. Okay, we will see how that works out in a short while. So this and this, those two equations, there's this one and this one here down at the bottom are the same thing, just expressing it now in terms of slightly different variables. This one is a difference equation, the other one is a closed form solution. Okay, and you get this. So for instance, if I wanted to calculate H10 here, H10 will be 0.8 H9 plus, well, delta n doesn't exist apart from n equal to 0, and this one doesn't exist apart from n equal to 1. Right, so H10 is 0.8 H9, but where's H9? You have to go back in here. H9 will be something in terms of H8, then H8 and something in terms of H7. So you're going to get H10 in terms of a whole series of things, something H9 plus something H8, and then you add up all of that, and you would get the same answer that you got if you were to plug 10 into this expression before. Yeah? All right. Okay. What about the input-output difference equation? Remember, yz is 8z plus x 8z multiplied by xz, which is what we have here. If xz is an impulse, then yz becomes 8z. That's my normal my normal signals and systems approach, right? So y is the transfer function multiplied by x, right? In either the S domain or the Z domain here. So same approach as before. Let's cross multiply. Cross multiply, so you will get yz into 1 minus 0.8 z minus 1 is equal to 5xz plus 2z minus 1 xz. You leave yz alone on one side and you bring everybody else on the other, and then you read off the inverse transform. So yz, so in other words, if I were to just write this here, this would be yz is equal to, bring that on the other side, it will be 0.8z minus 1 yz plus 5xz plus 2z minus 1 xz. And I can read off the transfer function directly from that. The inverse transform of this is yn. The inverse transform of this, the inverse transform of yz is yn, but because you have a z minus 1, will be yn minus 1, and of course you have the 0.8 here. The inverse transform of xz is xn, and multiplied by 5. And z minus 1 xz is xn delayed by 1, right? And then, of course, you multiply by 2, right? And notice that if I were to make xn delta n, then I have the same expression that I have here. Right? If I put xn equal to delta n, then I get this expression on this page. Right? So all of these are the same. You're following? Yeah?
Yes, sir.
Right, you just have to run it through with a little bit of maybe your own, just write it out again when you get a chance. So all of these are the same thing, right? Just different approaches to the same thing. So let's see now, if I were to draw this out as a sort of a data flow. Remember that that is a sequence of values. So yn minus 1 is yn delayed by a sample. Xn minus 1 is xn delayed by 1 sample period, and so on. So let's draw this out in a little diagram and see what we get. All right. We have xn, And then we also have xn minus 1, which is xn delayed by 1. Okay, so I'm putting a capital D inside of here. I multiply xn by 5, and the delayed value of xn minus 1, I multiply by 2. Okay, and then on the other side now, we have yn, and then we also have yn minus 1, which is this output delayed by 1, multiplied by 0.8. And then all of these, we have to add up. We have to add up this, this, and this. And that gives us yn. So in terms of the sort of, if you plot it out just as how values may be working, you have that sort of diagram that we have in front of you. So the processing sequence would be like this. If this was an actual, this is the input output for a system, right? So the system, we have the system. So we have we have xn coming in here, right? This has some transfer function, and we have yn coming out. So how the system works now basically is like this. Your first value comes in. The first value of the input comes in. Then is multiplied by 5. We don't have anything else. So the first value of yn goes out, which is simply 5xn. Then xn is shifted to n minus 1. Yn is shifted to yn minus 1. In other words, the past input and the past output are stored, right? So you hold it back. So you got the first input, we get an output. You store that first input, you store that first output, and then the next input comes in now. New xn is received. So the new xn now will give you 5 times the new xn comes in. It will multiply by 5. The old xn, the last value, will multiply by 2. We're going to add that. And the output that it had just before, it multiplies it by 0.8 and add that up, and then you get the output. Then that new output goes here. This old one goes to the trash bin. This goes to the trash bin. This one goes here. And then the third value of xn comes in. And so you keep going on. Make sense? Yeah? This is kind of like a digital counter. You remember when you had a digital counter, right? You have an input coming in, which is to tell it basically to go up and down, up or down. The output is a current value of the count. So it's storing that. When the input comes in, it checks count up, count down. So it will compare that, and then if it doesn't, it increments and it goes to the next state. So this is like a processing sequence where you're going from one state to another. Yeah? Everybody following? Let me know if you're not following. We all right?
Yes, sir.
Yeah, we're good.
All right. Okay. And so at the end of the day, you're implementing this. So if you look at it, notice that for each delay, we need to store at least one past output and one past input. So every delay requires at least one stored memory for the input and one stored memory for the output. And another thing, notice that it takes, because we have one delay on the input and one delay on the output, it takes at least one delay for the correct answer to come in. Notice the first time when X came in, it generated because we didn't have anything here. We didn't have anything here. So the very first value of xn was 5 multiplied by 5 plus 0 plus 0. So yn was simply 5xn. The next time it came in, is when we had a pass input and an output and it gave us the correct value. So for this system, the first value is wrong. It takes at least one cycle or one, because it's delayed by one, it takes at least one operation before the thing start to give you the correct answer, right? And that's the thing about discrete time systems. Depending on how many delays, and we of course each delay as we saw is related to a z minus something, right? The higher the number of delays is, the longer it takes for it to generate the first correct value, which is important. All right. This particular implementation of the data flow is something called the direct form realization of Yn. In other words, sort of as a straight programming, if you were to program this on a processor for argument's sake, what you have here is exactly how you would write it in code. Xn comes in and multiplies by 5, then you look at the answer, you delay Xn by, you store Xn once, etc., etc. For the diagram, what they've done for this representation of the transfer functions, they standardized the representation. So what we do is that normally each delay is represented by a box with a z minus 1 in it. The blocks that have these gain values in them, because they are gains, they use a sort of amplifier signal, a basic triangle, and they tend to put the value of the block inside the gain, whatever that is. So like the 5 or the 2 or the 0.8, they put it inside of the amplifier symbol itself, and then of course the summation signs, right? And I'll comment on this as we go along. Look carefully at the summation signs too. Sometimes they are minus signs, sometimes they are all plus, right? And we'll talk about this. This was generated in Simulink. This is how Simulink, if you were to implement a transfer function, and we'll see in a little while when you're doing the filter designs, you could generate the block diagram to see how the data flow is going. Okay? And these are the MATLAB symbols, but they have been standardized in books around the place. For our purposes, this is important. The delay block, you must use this. For the gain block, I have no problem with you using a box and putting the gain value inside of that. The summation, of course, is a circle with the plus signs on it. All right. So you're free to use either this, or if you're drawing it, you use a square. I've used both. This, you must use this. Okay. So any delay that you have in a transfer function block diagram representation, you must put z minus 1. All right. So comparing the transfer function and the diagram, you can see the gain inside of the amplifier blocks. The 5 is here, the 2 is here, the z minus 1 is the delay. So the 2z minus 1 is a delay, and then a gain of 2. All right, this one, you have the 0.8, z minus 1 means that there's a delay of 1, and that after that delay, whatever passes through the delay is multiplied by 0.8. So here you have it. Okay. Notice that in this particular one, they've put the minus sign here. I'll talk about that, and we'll decide on the two approaches. There are two approaches basically. You could put the minus sign here and put plus signs here, or you could leave this as all positive and change the sign on the summation block. You have to be careful because MATLAB does it one way. Books, textbooks, and online material, sometimes they interchange. So you have to watch. You have to really watch what is being done. As we go through, we'll standardize on a way that we we will on the approach that we will try to take. But you have to be vigilant if you're reading material to support what we're doing in class. Okay. Right. So let's get general now with it. A first order system with no initial conditions would have an input output. This is what a transfer function would look like. No initial conditions. So YZ is a transfer function. This is HZ by XZ. All right. And I've just expanded it. I've just put it in a slightly different form on the side here. I could now cross multiply it and then leave YZ on one side and bring everything else onto the other side of the equation and now draw that out. So the first order system, first order means that the order of the delays is 1, right? That's a maximum order of Z you're going to see will be -1. And once you map it out, cross multiply it, YZ is going to look something like this. Let's draw this out. We could draw it straight out from the diagram that we had. You put it here. Notice I'm using little squares here. So XZ multiplied by B0, then 1 delay, and it multiplies by B -1, and we add it up. Right? So we take these two and we add them up. YZ, you have the main output, but you also have a stored value of YZ that is multiplied by -A. So I'll put the -A inside of here. And you add that up, and then, well, this and this could be the same thing. I'll just put it here just to show you. All right, how the processing is basically doing. So is this plus what went on here. So I have a second addition block right here for you. Okay. This again is what we call the direct form realization or implementation, if you like, of the transfer function. Make sense?
Yes, sir.
Right. So a second order system, you have a second order system. So a second order system means that the highest order in the transfer function on the numerator and denominator, right, going to be 2. So how do you draw that out now? Same thing. Everything up until here was what we just had. This was the first order that we just drew. The second order one has an additional delay, and you multiply it by B2. And same thing with the output, an additional delay, and you multiply it by A1. Notice how we express delays. So one delay is Z -1. Z -2 is another Z -1 on the first one. So Z -3, a third order, would have had a Z -1 here again. Right? So each of them, that's why we retain the negative index and we make it simple. So you don't have to put like another block going here and put like Z -2 for argument's sake and whatnot. That's not how it works. Right? The processing, if you watch it, let me just clear that so it doesn't confuse anybody. If you watch it again, the first input comes in, is multiplied by B0, and it goes and you get the output straight off. That output is stored. That input is stored. The next input comes in, is multiplied by B0. The last input was multiplied by B1 and it added up. The last output is multiplied by -A and it added up, and then you get that. That value is now stored. The current value is now stored by so the old value is now delayed. The second old value comes in, delayed by 1, and so you keep going on. So in this case, you take 2 cycle times to get the correct answer. If we had a third order system, it would take 3 to get the correct answer. And so you keep going. Make sense? It's fairly straightforward once you look at it. All right. These are all called the direct form realization. In other words, as you get a transfer function, this is how you could implement it. It's not the most efficient way, as you'll see in a little while. But if you want a simple process, you have some data coming in and you want to manipulate it, this is how you take sample by sample processing, in other words. All right, so we have actually about 3 or 4 different ways that we could implement this in either hardware or software. The first, direct form, which is what we were talking about. As you get it, you do it, kind of thing. There's one called canonical form, which is the next thing that we're going to look at, which is a simplified version. It saves some processing, as you will see. Then cascade form and parallel form. All right, let's have a look at these and see how it works. If you go back to the transfer function here, you notice that you go to general transfer function. Let me just clear this again. Right. Notice that, yeah, back to the pen. Right. If you notice, all of the x's, the input x coming in here. So you have x coming in. Where am I? Right. You have the x's coming in, and they're all processed by these coefficients and delays, B1, B2. So this now is all going, the data going forward, and then the A, now this is outputs that are being fed back. So the B values with X are going forward, and the A values with the past values of Y are being fed back. In other words, the transfer function as it is has a feed forward structure, which are all the parts associated with X and the B coefficients, or the numerator coefficients, and the feedback structure, which are all the outputs and past outputs, and the A coefficients. In other words, all the denominator coefficients. Yeah? Fair enough?
Yes, sir.
Right. The feed forward path, in other words, this bit here, the feed forward structure, and I've gone, and here I've changed the symbol back, so I'll be using both of them, using a triangle for the gain instead of that. This feed forward, if you have a transfer function that only has a feed forward part of it, so in other words, the output is only a function of current and past inputs, the transfer function would look like this. Remember, the transfer function is numerator over denominator, right? This is 1. So this particular transfer function only has poles in it. Sorry, zeros. Parts on top. This is something called a non-recursive transfer function. In other words, no past values of n are used. You're only using current inputs and no past values of outputs. There are some kinds of digital systems that behave like that. So something like a counter that is permanently set to go up, right? It doesn't have a choice. It goes and it goes once you start it. This creates a transfer function with what is known as a finite impulse response. In other words, if I were to put the values of Z in, Y stops once Z is finished. There are no past values of Y associated with this. So you put in Z, once the Zs are finished, and it runs through all the old stored values of Z, that's it, thing stops. So you get a finite response with a transfer function like this. Transfer functions that have feedback are also called recursive. transfer function. So they're using past output values. So in this case now, because past output values of y are used, you tend to get results that create infinite impulse responses. Because even when you stop the input, the output is still using past outputs to calculate a new output. So every time it calculates a new output, it stores that and it keeps going on, going on, going. All right? This tends to create a response that goes on and on. Okay? So non-recursive gives you finite responses. Recursive gives you infinite responses. Yeah? So in general, a transfer function, a general form transfer function, is a product of a recursive part and a non-recursive part. And if you want to look at it differently, I could express it like this. So I have the yz is equal to b naught by w, and w is xz over the 1 plus a. So I've just broken it up. Fair enough? Right? In other words, I just said that this was b by w over a. Yeah? Where w is, if I put this, the w is x z by 1 over a. Make sense? Everybody following?
Yes, sir.
Right? So if that is the case, then remember we're dealing with LTI systems. I could do this in any order. In other words, as it is right now, I have y is all the b's and associated z's multiplied by wz, which is xz over a. Because in an LTI system, I could actually put it the other way around. I could have yz is wz multiplied by b. 2 by 3 and 3 by 2 is the same thing, right? Once is linear. So if I do it, then what I have done, notice this is the feed forward. And this is the feedback. I've swapped them, right? So in other words, I took this structure here because I could do it in any order because it's a linear time invariant system. I could swap the order of the processing. So in other words, do the feedback first and the feed forward after. And then if that is the case, this is what the processing looks like, right? And W is in fact this little bit in the middle here. Yeah? I haven't done anything too strange. Like I said, 3 by 2 and 2 by 3 is the same thing. Right? So I've swapped it to the feedback and the feed forward structure. Everybody with me? Yeah?
Yes, sir.
Hopefully. Right. This is the same direct form again, because as I get it, I put it down. But notice something here. Because we could, because LTI systems could be cascaded in any order, we can now use this particular arrangement to remove one of the setup delays. You remember when you had the original thing here, every one of these is storage. So this is storage. A delay, when I take a value and delay it, it means I have to hold it somewhere. Same thing here. So in this case, just for this one, I needed storage. I needed two places to store inputs, and then two places to store outputs. If I draw it here, this is the same thing. I have inputs here, Sorry, I've swapped it on the other hand. I need storage for input, storage for input, storage for output, storage here. But notice now, the stores are now related to an internal variable WZ. Why store WZ twice? So in other words, by swapping the feed forward and the feedback, I now have double stores for the same value. So I could get rid of this. I could eliminate one of the stores. In other words, I could free up half of my memory storage instantly by just getting, I don't need it any longer. So by doing it in this form, I could reduce the number of delays by 1, and we call this new structure a canonical realization. So it's another or direct form version 2. In other words, I have what I have done, take the transfer function, swap the feed forward and feedback paths, and removed one of the storage. So now I only need, if this was, let's say it was a 50 order system, before I needed 50 stores for input plus 50 for the output. By processing it in this way, swapping the feed forward and feedback, I have removed one of the memory requirements, and I only need 50 stores now instead of 100. Yeah? Make sense?
Yes, sir.
You're going to have to write it out again, like I keep telling you, however you want to do it. But get some paper on your on your notebooks and so on, and just write it out and convince yourself that the processing is working the same thing. It is linear, time invariant. So A by B and B by A is the same thing. All right? Okay. And of course, in the same example that we have here, if I were to generate it, and we'll talk about how to do that just for testing purposes, you could generate it in Simulink, and this is the direct form 2 or the canonical realization of the same example. One little business, MATLAB. By the way, the A's and the B indexing is standard. All the textbooks, all the software use it. Software, however, can index from 0. So you will find that B0 in the transfer function translates into B1 in MATLAB. B1 in your transfer function will translate into B2, and so on. All right? Just be aware of that. We went through that when we were talking about the little manipulations with the FFT and where the values were and so on. All right? Right. Now, just look at these other two. It's fairly straightforward to follow now. If I take a transfer function, I could take any transfer function like what we have up here, and I could factor it into first and second order polynomials. Right? So in other words, I could take, like how you were accustomed doing this with the Laplace domain. Same thing here. So I could take a higher order transfer function and express it, factorize it, and express it into a sum of a product, sorry, of smaller transfer functions, first and second order ones. This now, take the big transfer function and you express it as a product of smaller ones. It's called a cascade representation. So what that would do is that, for instance, the first order direct form would look like that for a transfer function. So the second order would look like this. We just did that. A third order would be this, where this now becomes the input here. So first multiply by a second will give you a third. Right? This now, if you implement a system like this, what you're doing is minimizing storage requirements. So for instance, if there's some sort of embedded application, for argument's sake, where you have, and we'll see it's not unusual to have filter orders of 20, 50, even 100, right? Each of those requires storage. If you don't have much storage, what you can do is to break up the transfer function into first and second order transfer functions, and you just process them in sequence. So you do one, then you feed it to the second. So for instance, this is third. A fourth would have had 2 and 2, right? A fifth would have had 1, 2, 2, sixth, 2, 2, and 2. So you see, you could create any order transfer function using first and second order sections. Yeah. This now minimizes your storage, but it takes longer to process because, of course, it has to do the first one, calculate the answer, and then that answer goes to the second one, and so on. All right. And there's some, this is an example here. You could run through the example and follow it. It's easy. Of course, the other one now, if I take the transfer function and I separate it into partial fractions, remember what partial fractions will do? Partial fractions create a transfer function that is the sum of the first partial fraction plus the second one plus the third. If I were to represent this now, this is what you call a parallel representation. So the transfer function comes in and is broken up now into, you come in here, you have, this is xz, you have transfer function 1, transfer function 2, transfer function 3, 4, right? These are all created by your partial fractions here. And then you add up the answer and you have it here. This is a parallel type processing. So factorizing gives you cascade, partial fractions give you parallel. This now is where you get the minimum processing time because it's going to do all of these together. Right? As the input comes in, it does all of the calculations in each transfer function together and gives you the answer. This requires more storage because you have to have storage for each of the transfer function in here. But if processing time is an issue, this is the kind of sort of implementation that you would want. So for something like where real time or close to real time is important, like a hearing aid, for argument's sake, you would want to do the processing time in parallel because there's less delay. But if you have something where processing time is not so much of a problem and you could wait a little bit for the result and the storage requirements are important for you, then you do it in cascade form. Yeah? All right. So in summary, what we did today, we looked at first off the general form of a transfer function, the transfer function, the data flow of the transfer function, a generic form has both a feed forward and a feedback path. The feed forward path creates transfer functions with finite responses. The feedback creates transfer functions with infinite responses. Transfer functions may have a combination of both of them. If you swap the feed forward and the feedback path, you create an implementation of the transfer function that requires half as much storage as before. And then if you want to process the transfer function, you can express it. If memory is an issue, then you take the transfer function and you break it up into partial fractions and you work it in cascade form, which is slower processing time, but less memory. If you need faster processing time and memory is not an issue, then you take the transfer function and you break it up into partial fractions. So the result will be part 1 plus part 2 plus part 3 plus part 4, etc. And you add up the results at the end. All right? Fair enough? Any questions? Well, I'm sure you have, but you need to run it through a little bit on paper and then see what the answers are. And then if it doesn't make any sense, then come and let me know. Yeah, everybody all right? Sort of?
Yes, sir.
All right, sort of. Okay, so look at it. The recording will go up, and on Wednesday morning, we're going to start looking now properly at filter design. Right? How to implement filters. If I give you a specification and you want to use that filter for some sort of application, how do I go about using it? Or getting a transfer function to behave the way I want it. Yeah? All right, so if there are no questions at this point, I will end the lecture here today. I'm in the process of marking the midterm, so let me see if I don't get too many interruptions between now and Wednesday. Hopefully, I'll be able to get the marks back to you by then. All right. Okay, everyone. So have a great day, and I will see you Wednesday morning, God willing. Take care.